we've been talking about logarithmic functions, and we didn't really do any equations or anything yet, just logarithmic functions and just evaluating them and stuff like that, how to switch between exponential and logarithmic because they are inverses of each other. And so one of the things we need to do is talk about the domain of logarithmic functions because it's a little bit different. Okay? If you recall, I told you that if you had log base a of x, that x had to be greater than 0. So for the basic form of a logarithmic function, the domain is going to be from 0 to infinity, and the range will be from negative infinity to positive infinity. So for a very basic logarithmic function where it's just x, the domain is going to be from 0 to infinity, not including the 0. We can also determine that because they are inverses of each other, the domain of the logarithmic function would be the range of the exponential function, which if you recall is 0 to infinity for the basic one. And the range of the logarithmic function is the domain of the exponential, which is all reals, negative infinity to positive. So that's for the very basic form of f of x is equal to log base a of x. Now, if our function is a little bit more complex, so f of x is log base 5 of x plus 2. I'm going to rewrite that because it's kind of there. That function's domain is not going to be 0 to infinity. It won't be that simple. The expression that we're taking the logarithm of, the x plus 2, that must be greater than 0. So just like we did for like even roots, remember the even root, we take the stuff inside the even root, they get greater than or equal to. Here we know the stuff that we're taking the logarithm of needs to be greater than 0. So we're going to set x plus 2 greater than 0. And then we're going to solve it. We're going to subtract 2 from both sides. And we'll get x is greater than negative 2. So that means the domain of that function, the domain of f there, is going to be negative 2 to infinity. Any questions on that? So let's try a few. We'll work these together. Don't have a lot of room for them. So we have these functions. We want to find their domain. I'm going to make us a new little slide to work with here. Oh no, there is a bunch of room. What the scroll one? There you go. Oh, why it's not there? It goes. So let's say for A, we have f of x is equal to log base 2 of x plus 3. Notice that we don't really care what the base is at all. There are some limitations for the base if somehow the base was a variable, had a variable in it. I don't think you'll see anything like that in this class. I know you won't see it in this class, but probably won't see that ever. But remember, that has to also be greater than 0, and it can't equal 1. So there are limitations on the base as well. But usually that's not going to be the case for anything. So if we're looking at log base 2 of x plus 3, what we know is whatever is here needs to be greater than 0. So we're going to say x plus 3 is greater than 0. Subtract 3 from both sides. And so x is going to have to be greater than -3. So my domain of that function would be -3 to infinity. Any questions on that? Let's do C next, because B's a little tough. So for C, I have h of x equal to log base 1/2 of the absolute value of x. Now, what we said is that whatever you're taking the log of, so in this case, the absolute value of x needs to be greater than 0. Is there anything I can take the absolute value of x of, and it won't be greater than 0? What do you think? We can set it up and work it out. No? Okay, let's see. So if you remember, back in the day, seems like forever ago, but we talked about inequalities with the absolute value, right? We said if you have the absolute value of something it's greater than 0, you're going to write that as two separate ones. All right, you're going to say, well, x could be greater than 0 or x could be less than 0. If x is less than 0, you take the absolute value of it, it's going to be greater than 0. If x is greater than 0, you take the absolute value of it, it stays the same, it's still greater than 0. Well, what number is missing there? Anybody know? You're saying that it's everything greater than 0, everything's less than 0. What's not accounted for? The 0. So for that function right there, you want it to always be greater than 0. If it was 0, it equals 0. So my domain for that function is going to be x such that x cannot equal 0. Because if x was equal to 0, you'd have log base 1/2 of 0, which we can't have. So that one's kind of tricky. It's a tricky one. And let's try B. We'll go with it. So we talked about this. I don't know when we talked about this, probably. We did inequalities. All right, so we have g of x is equal to log base 5 of 1 plus x over 1 minus x. And we want that to be greater than 0. So we want 1 plus x over 1 minus x to be greater than 0. What will make that greater than 0? If you have a fraction, what will make it positive? If you have a fraction, right? We have a fraction here. What will make that fraction positive? I'll give you one. It can either be positive over positive, right? That's gonna be a positive. But what else could it be? What if the numerator is negative and the denominator is positive? Would my fraction be positive? It'd be negative. What if my numerator is positive and my denominator is negative? That's gonna be negative. But what if they are both negative? Then it's gonna be positive, right? So we have two scenarios here. We got to take care of the one where they're both positive. That'll make it positive. And we have to take care of the scenario where they're both negative, because that will make it positive as well. So we're going to set that up. We'll do 1 plus x is greater than 0, and 1 minus x is greater than 0. And then for the negative one, we need to do 1 plus x is less than 0, and 1 minus x is less than 0. And we need to solve those and see if we get what we get. So if we do the first one, we'll get x has to be what, greater than -1, and if we add x to both sides, we'll get x is less than 1. So for that one, it has to be greater than -1, less than 1. So it has to be that interval for them both to be positive. Any questions on that? Let's look at the other one. Here we get x is less than -1, and we'll get x is greater than 1. Is that possible? Is it possible for x to be less than -1 and also greater than 1? You always draw it. -1, 1. We're asking if it's possible for it to be here and here. No, right? They don't contain the same area. So it's impossible for a number to be both less than -1 and greater than 1. So this cannot happen. So the only one we got to worry about is going to be this one right here. Oh, that's why I was looking at the wrong one. I was like, hold up. I got a different answer. Notes. I forgot we did them out of order. So that would be the only interval that would be allowed for this. Any questions on that? So whatever you're taking a logarithm of, it needs to be greater than 0. It needs to be positive. If it's a fraction, a rational function like we had here, you got to think about those two scenarios where it's positive over positive, negative over negative, and see how it's going to work out. If you get intervals that share an area, that's good. If you get intervals that don't share an area, they're disjointed, and you can't have a number in both of those. So they can't work. So that can't happen. It's not a possibility. All right. Any questions on that? Okay. Let's talk about the graphs. So remember that a logarithmic function is the inverse of an exponential function, or they are the inverse of exponential functions. And so their graphs are going to be symmetric about that or around that diagonal line. Okay. So if this blue line here is your exponential function, the logarithmic that goes with it is going to be symmetric with respect to that diagonal line. It's going to reverse the values. Instead of us having 0, 1, we're going to have 1, 0, just like we did for the other inverse function. Notice that one is exponential decay. Yeah. This one here, exponential growth. So this is the exponential function here. This is the logarithmic function. That's its inverse. So you can see instead of it having a point 0, 1, it has 1, 0. Instead of having a point 1, 8, it has 8, 1. So once again, it's going to depend on what the base is, because if the base is less than 1, it's going to be the inverse of an exponential decay function. If the base is greater than 1, it's going to be the inverse of an exponential growth function. So the shape will be different. I think I got a couple more here. Oh, these are actual examples. So this is y equals 2 to the x. It's an exponential growth function because my base is 2. And this is going to be its inverse, log base 2 of x. And so you can see how the order pairs are swapped here. Boom, boom. So if you ever have a hard time graphing a logarithmic function, which we're going to talk about how to do it in a little bit, but if you ever do run into trouble with it, you can find the exponential one, graph it, switch to order pairs. That's going to be your logarithm. And I like to show this one even though it's kind of confusing, but this is, the blue line is the exponential function 1/3 raised to x. So it's going to be exponential decay, right? And so my logarithmic function is going to be, the inverse of that is going to be log base 1/3 of x. And so its graph will look like this right here. Notice the points are swapped. Instead of -1, 3, you have 3, -1. 0, 1, you have 1, 0. 1/3, 1. Oh, nope, that's the wrong one. This is from the exponential. 1, 1/3, you'd have 1/3, 1. The exponential decay ones look confusing quite often because the two graphs cross each other because of the way that they're set up. That'd be an interesting little, figure out where do they intersect. I mean, it's outside the realm of this course, but it'd be interesting problem. All right. So remember, still your base either has to be between 1 and 0 or greater than 1. It can't equal 1. It has to be greater than 0. All right, let's try one out. So we have log base 2 of x plus 1. Now, we're going to do the same thing that we've always done the graph stuff. We know kind of the shape because we know that the a value here, the base is 2. So we know that its exponential function would be exponential growth. So we know that ours should be the mirror image of that of the diagonal. So it should come up and then kind of level off. So we kind of have an idea of what the shape is, but we don't know the points. And so we need to find those points. And this is where most people have difficulty. So I'm going to talk to you about how to do it, though. So we're going to do x's and y's. But we need to be a bit careful about our x's. And I'm just going to choose one for example, just to show you how things can go wrong. But if I say, well, let's let x be 2. That means to figure out what my y value is, I need to do log base 2 of 2 plus 1, which is log base 2 of 3. If you recall what logarithms mean, that means I'm trying to find what? Anybody remember? No? Anybody want to remember? I'm trying to find what power do I need to raise 2 to get 3? What exponent put on a 2 will give me 3? That sounds a lot better, other than saying 2, 2. What exponent do I need to apply to a 2 to get 3? Is there anything? I mean, there is one, but I mean, we can't figure it out, not just in our heads. And so that's a bad point to use. So what I need to think about is that I want to make sure that 2 plus 1, when I add, not 2 plus 1, x plus 1, sorry. when I do my x plus 1, I want to make sure that I can write that as 2 to some power. So I need to think about my x values. Okay, so this is a bad x value. All right. We'll just put an x on it. Bad x value. So what do y'all think we can use? Anybody have an idea? 3. All right, let's try it out. So if we do 3, that means we're going to do log base 2 of 3 plus 1. Oh, that's a 3. Let me fix that. Which is going to be log base 2 of 4. What power do I need to raise 2 to? Or what exponent do I need to apply to 2 to get a 4? 2. So that means that when x is 3, my y is going to be 2. So now I got a point 3 comma 2. Good. 3 was a good one. Of course, I want more than 1 point, right? So what else can we use? Anybody got another one? 5? Let's try it. I don't know about 5. Let's see. So that's going to be log base 2 of 6. So can we raise 2 to some power and get a 6? I don't think that's going to work. Right? Because we have 2 squared is 4. What's 2 to the third? Anybody remember? 8. So that one's not going to work. But if we know that it could be 8, let's do 7. Right? Because we're adding 1 to it. So we're going to do log base 2, 7 plus 1. That is just a really bad 7. I'll fix that. Which is going to be log base 2 of 8. What power do I need to raise 2? What exponent do I need to apply to 2 to get 8? 3. So I know I have another point, 7 comma 3. All right, so we got 2 points. I should have did that. Oh well. What's another point we can use? Let's say we're going too far on the right. Let's think about some stuff more to the left. So stuff that's less than 2. What could we use?
Could you do the opposite, like -3?
All right, let's try -3. Nothing wrong with trying it, even if it doesn't work out. Let's see. So we're going to do log base 2 of -3 plus 1. Log base 2 of -2. Is there a problem with that? When we take the logarithm of something, what does it need to be? It always needs to be greater than 0, right? So this is undefined. We don't even know how to find that. That's not going to work for us. But you're on the right track. You just want to look too far. If we did -1, we get 0, but you can't raise 2 to something and get 0. But what if we make x 0? Then we do log base 2 of 0 plus 1. That's log base 2 of 1. What exponent do I need to apply to 2 to result in a 1? Anybody remember? It's a property. What's that? 0. Yes, good. So we have a point 0, comma 0. And there's one other point that wouldn't be hard to work with. I mean, you probably don't need this many, but just to, exhaust what we can do. But if we did 1, log base 1 plus 1, so we'd have log base 2 of 2, which what exponent do I need to apply to 2 to get 2? If the base and what you're taking a logarithm of is the same, it's just going to be 1. And so we have the point 1, comma 1. So we have these points 3, 2, 7, 3, 0, 0, 1, 1. Let me write those down. So those are the points we got. Any questions on finding the points? See, you have to be very selective on what you're going to choose for the x, and that's what makes it tough. You kind of got to think backwards a little bit, and people are struggling with it, but it's not, any other way to do it. I mean, the other way to do it is you could say, well, if that's my function, then its inverse would be 2 to the x plus 1, right? And so we could figure out some points from there and then flip them around. This should work out, right? Unless I messed that up. But yeah, you could do that. I think that's what, oh, it might be. Yeah, I might have messed up when I did the inverse of it. I mean, we could find it. What is it? Y is equal to log base 2 of x plus 1. Just because I don't want to give you all false information. And so if we switch our variables here, it would be x is equal to log base 2 of y plus 1. And if we switch that to exponential, let's write it the other way. This would be 2 to the x is equal to y plus 1. Yeah. That's what I thought. And so it would be 2 to the x minus 1 is equal to y. That would be your inverse function. I tried to do it quickly in my head. That was a mistake. So you could find some values, some order pairs for that function, and then just reverse them, which should give us those same values. Let's see. 3, 7, yeah. 2, 3, yeah. So that's another strategy. If you ever get blockaded, use what you know about inverse functions and exponential functions. All right, so we got these points, and I didn't put a graph on here because I wanted to kind of draw it by hand, same as you would have to do. So we need at least 7 going forward. What is the domain of our function actually? That way I know how far to go. Well, we know that x plus 1 has to be greater than 0, so x has to be greater than -1. So I know my lowest x value can be -1. So that kind of gives us something to start with. Could have did that earlier too. Think about it. And so let's say this is 7, 6, 5, 4, 2, 1. I ran out of room a little bit there. And 2, 1, 2, 3, 4, 5, 6. we don't have any negative values, so I don't think we need to do anything. So let's see what we get. Let's see what we get, and we'll try to see if we have enough. So the first point, 3, 2. So x is going to be 3, y is going to be 2. Put a point right there. Next point is 7, 3. That's going to be x7, y3. We got 0, 0. And we got 1, 1. What about that? Now, we know that x being -1 is the domain restriction. It can't be -1 and it can't be less than. So it has to be greater than -1. So what do you think is going to happen at that point? At that x is equal to -1 area? Is my graph going to come like this and then go, whoop? Well, this would be a problem here, right? Because it would be less than -1. So we can't have that. What do you mean by intersect?
I thought it would like meet in the middle or on a point like that.
So it's gonna hit these points for sure. But what is it gonna do after that?
Go down.
It's gonna go down. But what do you think it's gonna cross? It won't cross over this -1 here. So what you're gonna have is a vertical asymptote. It's gonna get closer and closer to that. And then go down. And that is gonna be our logarithmic function. And I imagine the exponential function, we could graph it. It would have 7, 3. No, 3, 7, sorry. So here, we'd have 2, 3. We have 0, 0. So my exponential function probably come like that. So that would be the inverse there. But you don't need to graph that. I'm just showing it to you so you can see the relationship there. And for y'all, I mean, when you're working on the homework, you're just picking the graph. You're not actually graphing it. So if you could find some points, you could probably get it. But it's not a bad skill to have to understand how to actually draw it. So when you have that domain restriction, that's going to give you some type of, remember for the exponential functions, we had horizontal asymptotes. So since we're inverting the functions, it's going to be a vertical asymptote. All right. I'll give y'all a moment. Try this one out on your own. See what you can do. I would suggest finding a domain first and then picking some points and see if you can get that graph. So give it a shot. I'll give you a few minutes and then we'll talk about it. Real quick. Okay. Cool. Sorry, I just wanted to see if I had that on there. Thought I did. That's log base 3 of 1 minus x. Say, well, what is the domain of my function? That's going to tell me what x values can I even choose from, and then we'll narrow it down from there. Well, we know that 1 minus x needs to be greater than 0. So if we add x to both sides, we get 1 is greater than x, which means x has to be less than 1. So you can't have 2, you can't have 3, you can't have 4. It's got to be 1. Well, not even, it can't be 1. It's got to be less than 1. So our domain here will be negative infinity to 1. And so if we're choosing our x values, see what y's we get. First one I would try, let's try 0. All right, so if we do log base 3, 1 minus 0, that's going to be log base 3 of 1, which if you have log base anything of 1, is going to be not 1 at all, it's going to be 0. What exponent do I need to apply to 3 to get 1? 0. So I know I got a point 0, comma 0. What else? What's some other points you think we can use? -8. Let's see. Log base 3, 1 minus -8. Oh yeah. So we have log base 3 of 1 plus 8, which is 9, which is going to be what? 2. So at the point -8, comma 2. All right. What else could we use? That's pretty large, right? Yeah. Well, we did, think about it in terms of exponentials, we did basically 3 to 0. We did 3 squared. Well, can we figure out what it would be for 3 to the 1? Can we make what's in here just 3? What if we do -2? So we'd have log base 3 of 1 minus a -2. It would be log base 3, 3, and that's going to be 1. So it's growing pretty rapidly because we got, I mean, it's got a base of 3. Anytime you get a base of over 2, it just seems to take off pretty fast. So, and we can't do anything greater than 1 or 1 itself. And I think those are the only ones that are going to work out. So yeah, I think the next one would be pretty tough. So let's stick with these 3 points and see if we can figure it out from there. So we got 3 points of 0, comma 0, -8, comma 2. Oh, let's write them in the other order. -2, comma 1, and -8, comma 2. It doesn't really matter if you write them in a order. I just like to have things in order. All right, so how big does that graph need to be? Well, the y doesn't have to be very large, but the x's needs to at least go to -8. I usually try to draw mine as square as possible, and we'll add to it if we need it afterwards. Let's say 1, 2, 3, 4, 5, 6, 7, 8. Oh, that's supposed to be an 8. That moved a lot. Moved it while I was right there. There we go. And we know that the highest x value we should have is just 1. It's going to get stopped there. We know we're going to have, we should have a vertical asymptote there. And so our graph should be all over here somewhere. So let's put our y values 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So the first one we got 0, comma 0. That was easy to do. Right to word it. Next one we got is -2, comma 1. That's going to be here. And then we have negative 8, comma 2. So it looks like how our other graph did like this, right? Looks like this one's going to be backwards. It's going to come and then go down. So it's going to come from the left and then swoop down at that vertical asymptote. And so what we're going to end up with, I'll try to draw as best I can, something like that. There we go. If I had to guess, I better not guess again. I was going to guess the exponential function. If you wanted to find the exponential function, you could. You know, just do your normal inverse function properties and switch it from logarithmic to exponential. Get you there. So if you want to do that, you could. Any questions on that? Do a 2, negative 8. Maybe way down there. I'm just thinking about what it's going to look like. Yeah. All right. Leo. Oh, hold on one second. I got to get that off the screen. All right, so let's talk about some properties. We did this for exponentials, and so it's worth looking at for logarithmics as well. And it will help you with the graphing a little bit. The domain we already talked about. So the basic exponential, the basic logarithmic function, its domain is going to be from 0 to infinity, not including the 0. Its range is going to be all real numbers. Now that they may shift, like we saw, right? We have one where it had to be less than 1, another one where it had to be greater than negative 1. That 0 to infinity can shift. That negative infinity to positive infinity, that won't shift. It can shift wherever it wants, but it's still going to be negative infinity to positive infinity. The x-intercept is going to be 1, and there is no y-intercept. That can also change because if we look at the shifts that we just had, our x-intercept was 0, 0 here, and our y-intercept was 0, 0 here. That's the same for this one, actually, oddly enough. So that stuff can shift and change. It just depends what happens with the graph. So that's why I don't put too much value into trying to memorize this stuff, but it's good to understand what's happening. The basic logarithmic function is decreasing if a is less than 1, and it's increasing if a is greater than 1. So I think I have a graph on both right here. This is if it's greater than 1. Notice it's increasing now. When you had the exponential, it like took off, boom, right? For the logarithmic, it starts off fast and then it slows down its increase. Okay. If a is less than 1, it's going to decrease, and it's going to decrease fairly quickly and then slow down, whereas the well, I guess that's kind of the same. The exponential would decrease quickly and slow down here. I guess because the way you switch it diagonally, it still decrease rapidly, and then it slows down. And these are some points. If it's a basic one, you're going to have 1, 0, a, that's your base, comma 1, and 1 over a, negative 1. But like those can shift. I don't put a lot of work into memorizing that. The graph is smooth and continuous with no corners or gaps. That's good to know. So it's a continuous function. There's no jumps. There's no gaps in it. It's a smooth function. You can draw it with one pencil stroke. Remember, if you have the natural log of x, that means that x is equal to e to the y. That's the inverse functions of each other. The natural log of x, and x is equal to e to the y. That's, well, basically, this is if you're switching it to exponential form. And so you can see both those functions here. This is the exponential function with base e. This is the logarithmic function with base e. And so, oh yeah, this will get closer and closer. You'd have a vertical asymptote right there. You can see how they're symmetric with respect to the diagonal and just the points and stuff like that. you can get these values if you want. I don't see any point in that. I just like showing them so you can see. And then we got the common logarithm. There it is. So if you have y equals log of x, this is what it's going to look like. You're going to have a vertical asymptote. Once again, x equals 0 for that one. And since it takes off, the exponential takes off super fast, this one's going to slow down super fast. And it's going to slow down and barely increase as it keeps going to infinity. So those are the functions there. Those are the main ones, you know, base 10, base E, that you'll see in the real world. And that's what their graphs look like. All right. Now, let's talk about some equations. So there's two types of logarithmic equations you can see, or that you will see. And it's similar to, the first one's similar to the exponentials. So one that you can see is, say, like you have log base 3 of x plus 1 is equal to log base 3 of 2x. Let's make this. Sorry. I'm making sure that it works out. Well, let's see if it does. So what do you think you're going to do to solve this one?
Oh, so x plus 1 equals 2x.
There you go, because they both have the same base, right? And it's just like when we had two exponentials, they had the same base on the side, and we can just set what their exponents were equal to each other. Same thing here. So we can make this x plus 1 is equal to 2x. And so we subtract 2x from both sides. I get negative x plus 1 is equal to 0. Subtract 1. Negative x is equal to negative 1. And thus, x is equal to 1. Now, once I solve that, I do need to go make sure that that value is in the domain. I need to plug it in for all of my logarithms that I start with. And go, okay, well, is 1 plus 1 greater than 0? And is 2 times 1 greater than 0? Those will both check out, and so that is a valid solution. We're good to go. If you get that it's equal to 0 or negative, then that's not a valid solution. That's an extraneous solution, just like we have the radical equations earlier in the semester. Same situation here. They are a solution to the equation that you end up with, but not the original equation, because they're not the domain. Any questions on that? Quick example of that. I have one in my head, so let's see if it works out. Let's say log base 6 of 4x plus 2 is a log base 6 of x. So once again, we have logarithms. They have the same base. One log on each side is equal to the other. One log on one side is equal to the log on the other side. So that means that what you're taking the logarithm of must be equal to each other. So 4x plus 2 has to equal x. So if we solve that up, see if I did this in my head right. So we have 3x plus 2 is equal to 0. Let's subtract 2 from both sides. We get 3x is equal to negative 2 divided by 3. We get x is equal to negative 2/3. But if I plug that negative 2/3 in here, it's going to be log base 6 of negative 2/3, which is going to be undefined. So this is not a valid solution. So if my only solution is not valid, it's going to be no solution. Okay, you'd also have to check it here, which would be, I don't know, negative 8/3 plus 2, which is going to be negative as well, I believe. Huh? Yeah. So, but if it fails any of the logarithms domain, it's not a valid solution. Any questions on that? Good. All right, so this is where we get into the difficult stuff. What if it's not a logarithm on both sides? What if it's log base 3, 4x minus 7 is equal to 2?
You have to figure out how to get it to log on that side.
You mean have it like somehow getting the logarithm on the right hand side? How do you think we would do that? I guess you could. But how would you get log base 3 to be 2? I don't know, huh? It's a good idea. I never thought about that. How could you? No. But that's not the way we're going to go about it. I'm just wondering if that is a valid way to do it. What else do you think we could do? Anybody got an idea? Can we switch that up somehow?
Or you could do like the opposite of it.
What do you mean?
Like, no.
I think you're on the right track.
You know how like when you do the opposite of the log?
Mm-hmm. What's the opposite of a log?
I don't know.
The inverse of the log is the exponential, right? Exponential form. So if we switch this to the exponential form, what is it going to be? The base is going to be 3 raised to the second power is equal to 4x minus 7. So we're going to have 3 squared is equal to 4x minus 7. Can we solve that?
Yeah.
That's not too bad, huh? So 3 squared is 9. So 9 equals 4x minus 7. And then we're going to what? We're going to add 7 to both sides. Okay, I thought it wasn't going to work out. We're going to 16 is equal to 4x divided by 4. And x will equal 4. Now, we still need to make sure that's in the domain of our logarithm. If we plug a 4 in there, we're going to have 4 times 4, which is 16 minus 7, which is 9. That's good to go, as long as it's positive. Any questions on A? They're both A again. Any questions on the first one? Any? So let's look at the second one. Notice the second one's a little different, right? The x is in our base. And I said we would never see one like that for the functions, but for the equation, might. And so we're going to do the same thing. We're going to take that logarithmic equations, switch it to exponential, and you're going to get x squared is equal to 64. We know how to solve that, right? Take the square root of both sides. It's going to be plus or minus on that right-hand side. So it's going to be x is equal to plus or minus 8. That's the square root of 64. Are both those valid?
No.
Why not?
Because one of them is
One of those negative. Remember, the base has to be greater than 0 and not 1. So the only solution for this is going to be x is going to be 8. Any questions on that? No. All right, so remember for exponentials, all we did was learn how to solve ones that had the same base, right? They always had the same base, and we were able to get a single, base raised to some value on both sides, so that made equal to each other. We did the same thing for logarithms, but we also looked at logarithms where they weren't like that, and we were able to solve them by switching them to exponential. And so now we know how to do that for exponentials as well. If you have one that you can't represent in the same base, you can switch it to a logarithmic and work it out from there. So here I have e raised to the 2x is equal to 5. And there is no way that I could represent e and 5 in the same base. I have no idea how to do that. And so what we're going to do is switch this to a logarithmic. If you switch this to a logarithmic, what will it be? What's the base? E. E is my base. So we're going to have log base e of what?
12.
Log base e of 5 is going to equal what? 2x. Yeah, good. Good. And how can I write log base e of 5? That's another way for me to write that. Anybody remember?
The natural log?
We use the natural log. So we can write that as the natural log. The natural log of 5 is equal to 2x. And can we solve for x here? If you weren't looking at a logarithmic at all, you just had 2x, what would you do? Divide by 2. Yep. So x is equal to the natural log of 5 divided by 2. That would be your exact answer if you want to get an approximate answer. You can open your calculator. There is a key on your calculator. About where the e to the x one is usually in the same region as that, it says ln, the natural log. So you can do the natural log of 5 and then divide it by 2 in your calculator. Just make sure you close that parenthesis on the 5. That's why I wrote it out like that. And you get that x is about, and let's round to like, I don't know, 2 decimal places, 0.80. Is that what I did there? I did 0.805. I did 3 decimal places, so stick with that.